Hello everyone, welcome to Automation Community. In this video, we are going to learn about the 4 to 20 mA current signals. After completing the video, you should be able to understand the basics and the history of 4 to 20 mA current signals. The learning objectives of this video are: industrial history, why we use 4 mA to 20 mA as a standard signal, advantages and disadvantages. In the olden days, industries were equipped fully with mechanical operated devices like pneumatic sensors and controllers. Pneumatic means pressure. Pneumatic devices use pressure as a medium for the measurement and to control applications in the industries. The pneumatic devices generate an output signal in the range of 3 to 15 pounds per square inch. The 3 pounds per square inch represents 0% of the measured process variable. The 15 pounds per square inch represents 100% of the measured process variable. Pneumatic devices are bulkier, need compressed air for operation, higher maintenance costs, and takes more time for troubleshooting and repair. In the 1950s, with the evolution of electronics, the analog transmitters started replacing the pneumatic transmitters. The analog transmitters generate an output signal in the range of 4 to 20 mA. The 4 to 20 mA signals solve many issues, provides simple installation and configuration of field instruments. During the 1970s, the evolution of digital systems started with the introduction of programmable logic controllers, PLC. Now let's discuss a pressure transmitter with 4 to 20 mA current output. Assume a pressure transmitter is configured with a range of 0 to 10 bar. 4 mA represents the 0% process variable and 20 mA represents the 100% process variable. In this example, 0% of the process variable is 0 bar and 100% of the process variable is 10 bar. Consider a simple PLC example in which a pressure transmitter is connected to the PLC. The pressure transmitter measures the process pressure and generates an output signal in the range of 4 to 20 mA. The PLC is also programmed similar to pressure transmitter with the same range, that is 0 to 10 bar. The PLC calculates the received milliamperes into the equivalent pressure and displays it to the operator. For simple understanding, apply the process pressure in terms of 0%, 25%, 50%, 75%, and 100% to the pressure transmitter. If the process pressure is 0%, that is 0 bar, then the pressure transmitter sends 4 mA to the PLC, and it displays 0 bar pressure to the operator. If the process pressure is 25%, that is 2.5 bar, then the pressure transmitter sends 8 mA to the PLC, and it displays 2.5 bar pressure to the operator. If the process pressure is 50%, that is 5 bar, then the pressure transmitter sends 12 mA to the PLC, and it displays 5 bar pressure to the operator. If the process pressure is 75%, that is 7.5 bar, then the pressure transmitter sends 16 mA to the PLC, and it displays 7.5 bar pressure to the operator. If the process pressure is 100%, that is 10 bar, then the pressure transmitter sends 20 mA to the PLC, and it displays 10 bar pressure to the operator. Let's discuss why we do not use 0 to 20 mA as a standard signal. It has a dead zero problem. What is dead zero? Let's discuss this with a simple example. Take a pressure transmitter with 0 to 20 mA output connected to a PLC. The transmitter is configured with 0 to 10 bar. Pressure transmitters sends 0 mA to the PLC when process pressure is 0 bar and sends 20 mA when the process pressure is 10 bar. Case 1. Assume the process pressure is 0 bar, so the pressure transmitter sends a 0 mA signal to the PLC. PLC displays 0 bar pressure to the operator. Case 2. Let's consider a fault in the pressure transmitter loop. The fault may be a broken wire, faulty transmitter, noise, high wire resistance, or any other problems. For our discussion, let's assume that the wire is broken between PLC and transmitter. Consider the process pressure is 5 bar. Because of the broken wire, the PLC has 0 mA at its input instead of 12 mA. The PLC thinks that it receives 0 mA and displays 0 bar pressure to the operator, but in reality, it has to be 5 bar pressure. This is the dead zero problem. If the transmitter or loop is dead due to any reason, the PLC shows faulty readings. If the current signal range started from 0 mA, then it is not possible to differentiate the real process variable and the faulty reading. Remember, we are discussing the olden days PLCs which do not have features like diagnostic circuits, fault identification, etc. How to solve this dead zero problem? The solution is simple: start the current signal range with some value instead of 0 mA. So, we choose 4 mA as the starting value. Now let's discuss it with a simple example. Consider the same pressure transmitter example with 4 to 20 mA output current. Case 1. Assume the process pressure is 0 bar, so the pressure transmitter sends a 4 mA signal to the PLC. PLC displays 0 bar pressure to the operator. Case 2. Let's consider wire is broken between PLC and transmitter. Consider the process pressure is 5 bar. Because of the broken wire, the PLC receives 0 mA, and identifies it as a faulty signal. How PLC identifies the fault here? With 4 to 20 mA current signal, the 4 mA is the minimum current signal, which represents 0% of the process variable. For any faults, PLC receives 0 mA. So that faulty signals would be easily identified by the PLC. This advantage is called live zero. We discussed the disadvantage of using 0 mA and the advantage of using 4 mA. Now, you must have a question. Why 4 mA? Why not 5 mA? Why not 6 mA? Why not 8 mA? The first reason is, in the olden days, the power consumption of analog devices was pretty high. The analog transmitters require a minimum of 3 mA current for their operation. So, we have to consider the starting range from above the 3 mA. The second reason is 20% bias. The engineers followed the 20% bias as one of the factors for selecting the 4 mA. Calculate the 20% bias for the standard 3 to 15 pounds per square inch pneumatic signal. 20% of 15 pounds per square inch is 3 pounds per square inch. So engineers followed the same rule for the current signal. 20% of 20 mA is 4 mA. This 20% bias rule helps the engineers during the transition from pneumatic devices to analog devices and reduces the design complexity of devices like pneumatic to current converters and vice versa. Now you may have a question. Why 20 mA? Why not 25 mA? Why not 30 mA? The reason is, in olden days, 30 mA is considered as a dangerous threshold limit to the human heart. So, we have to select a value below the 30 mA. A ratio of 1 to 5. This is one of the major reasons for the selection of 4 to 20 mA current as a standard signal range. We have a very big advantage with a ratio of 1 to 5. The industrial transition from pneumatic devices to analog devices is not simple. Every industry was using pneumatic devices, and were operated with 3 to 15 pounds per square inch signals. We need to design the analog equipment to handle the existing 3 to 15 pounds per square inch signals and eventually replace the pneumatic devices with analog devices wherever possible. So design engineers decided to use a ratio of 1:5, which helps them to design the equipment with better accuracy and linearity. Initially, for a short period of time, they had chosen 10 to 50 mA as the signal range. This range is using 10 mA to represent 0% process variable, and 50 mA to represent 100% process variable. As discussed previously, the higher signal range must be below 30 mA, so eventually, they stopped using the 10 to 50 mA range. Next, they had chosen 4 to 20 mA current as standard signal range. It has an advantage of ratio 1:5. 4 mA higher than the analog transmitter minimum current. 20 mA is lower than the dangerous threshold limit of 30 mA. This range simplifies the design. One of the main advantages of using 4 to 20 mA signals is, it simplifies the signal conversions from current to voltage. A simple resistor is sufficient to convert the 4 to 20 mA signals into the equivalent 1 to 5 volts. Remember, we need a 250 ohms precision resistor for the conversion. Let's see the example of signal conversion. Basic formula to calculate voltage equals multiply current with resistance. Multiply the 4 mA with 250 ohms resistor to get 1 volt. Multiply the 20 mA with 250 ohms resistor to get 5 volts. So, it's easy to perform calculations and conversions. Now, you must have a question. Why do we need to convert the 4 to 20 mA into voltage? The 4 to 20 mA signals are connected to analog input modules of PLC. The analog input module consists of analog to digital converters, ADC. This ADC needs voltage as input signal and converts them into the equivalent binary signals, ones and zeros. Then analog input module provides the equivalent binary signals to the PLC processor, CPU, for further operations. Another advantage is current signals are more immune to electrical noise when compared to voltage signals. So the amount of noise or external interference is less. One more advantage is current signals can travel a longer distance. 4 to 20 mA signals can travel approximately 1 km, when the nominal power is 24 volts DC supply. Now 4 to 20 mA signals are being used everywhere. It's a standard signal choice for industrial users. It makes the installation and configuration very easy. External disturbances are very less. With the help of Live Zero, we can easily detect the faults. We do not need any complex equipment for troubleshooting these signals, a simple multimeter will do the job. We have two disadvantages. The first one is, the current signals may induce small magnetic fields in the straight wires. This magnetic field may affect the current signals traversing in the wires. To avoid this problem, we use twisted pair cables. We need a minimum of 2 cables, means 1 set of pair. This cable pair is twisted as shown in the right side image. By using the twisted cables, magnetic fields induced in the 2 cables are cancelled against each other, and resolves the magnetic field problems. The second one is, each pair of cable carries only 1 process variable. We discussed the reasons behind the popularity of 4 to 20 mA signals. Do you have any questions? Share with us.